Alright, so let's start. Today's topic was going to be work energy. Now, I would prefer the more apt name for this topic as the work energy theorem, and as we go along, I think you will realize why I won't emphasize on this word work energy theorem. But first, let's set the stage with a little bit of revision of the mechanics that we know. Alright, so in all of mechanics, the story always starts with what is known as a free body diagram. And I think over a period of the last 2 years, we are pretty comfortable with this. And anyway, I just want to mention this because we're going to draw a lot of free body diagrams as we go along. So what do we know? And just remember that we are doing a very simplified analysis over the last 2 years and also in this year. That is, we'll consider motion in one dimension. Okay, and also we will consider the force being a constant force, and by constant I mean constant in direction and also in magnitude. Okay, so let's go over these things one more time. So what do you mean by motion in one dimension, and what do you mean by a force being a constant, direction and magnitude? So what I mean is that we'll be able to keep track of this particle which is moving by drawing one axis, which maybe we can call as the x-axis, and we'll keep track of the particle by telling the x coordinate by some chosen origin. So we have an observer who keeps track of this particle, and he tells us where this particle is by telling us the x coordinate of this particle at different times, and we represent it by this notation. What it means is that I can tell you the x coordinate if you tell me the time. Now the particle is always on the x-axis, so this is this is what I mean by motion in one dimension. Next, we are saying that the force is constant. Force is constant. Okay, now what this means is, as per Newton's law, F is equal to ma. So the force is constant, and therefore the acceleration, which is also a vector, and the force is also a vector, is a constant. And this is the kind of motion that we are considering. So given that the force, the motion is in one dimension, that's the first point, and that the force is constant, which means that the acceleration is constant, what do we know and what can we predict? So this we learned last year, that we have with us two kinematic equations which we studied last year, and I quickly want to write them here again so that you remember them. And the first one is actually just the definition of acceleration. So once again, I keep reminding you that a is constant, and if a is constant, then one can write such an equation like this: v final minus v initial is equal to a, which is a constant, into the time. Now often in the textbooks it's written as v minus u is equal to at, and maybe we should stick to this as well. So this is our first kinematic equation, which is just the follows from the definition of acceleration. But we derived a more I think insightful, depthful second kinematic equation, and that looked like this. I'll just write it as u t plus half a t square. Now when we studied in the class, we wrote the left hand side as the final position minus the initial position, and but you could this is also what we mean by the final position versus initial position is that this somewhere some coordinate at the end of the motion is the final position, some coordinate at the beginning of the motion is the initial position, and mind you, these are measured from the origin, and that's why we just call it as a vector. And this is also measured from the origin, and since it has the direction and magnitude, we call it as, in fact we call it as a position vector. And these are the things we studied last time. So we prefer to call the displacement in the form of vectors. Alternatively, I can just write it as a displacement is equal to, for constant acceleration, is given by ut plus half at square, but in the textbooks you will find this as s is equal to ut plus half at square. Maybe it's a good idea to just call it as displacement. So this was our second kinematic equation, right? So this is a quick revision of what we already know, and this is the x-axis, the coordinate system, and the observer who's keeping a track of these particles by mentioning where his origin is. Now let's set the stage for our chapter, which I remind you is actually a very beautiful and important chapter in mechanics, the work energy theorem. And we can set the stage for the importance of this theorem and how it follows by considering a very standard example. But before I come to the example, I want to tell you that this particular example can be solved with our two kinematic equations. Just watch this, right? But also want to remind you that this theorem also we are looking at it in a simplified way, and what I mean by in a simplified way is that we are looking at it for one dimension. I think you know what it means now, and for a constant force. The theorem has got an existence in much more general conditions, but might not be a good idea to talk about that right now. So wanted to keep on reminding you that we're looking at it in a simplified form for our syllabus, and what do you mean by the simplified form? So now let's get to the standard example. Now the example that I'm considering is a very nice example of this, both these conditions, one dimension and constant force. So for example, the force on a particle of mass m is mg, almost a constant if you're not too far away from the surface of the earth. And here I'm considering a tall building, maybe around 100 meters high. Okay, so we just mark that down, 100 meters high, and from the top of this building we're going to let a stone fall, and it falls down 100 meters and hits the ground. So what's the question? Well, there can be many questions, but for this particular chapter the question is very specific and a very reasonable question. So I'm going to write down this question. This is going to be the central role for us in trying to understand this. What is the velocity of the stone when it hits the ground? So this is the question. Now what's so special about this question? I'm going to highlight now what's so special about this question, because it is something that we have to constantly keep at the back of the mind in this chapter, and that is, there is no demand on any information on time. Okay. So let me highlight that actually, that the question doesn't seem to care about time. Okay. So when we talk about work and energy, we realize that the question is not asking us information about time. Anyway, given that we are having the two kinematic equations, can we solve this problem? So before that, let me mention here that the acceleration is constant, and let's just take it as 10 meters per second square, the value of g. Okay, minus g if you want, but right. So as it turns out, we can actually solve this problem in two steps by using the equations that we already have. V is equal to u plus at, and s is equal to ut plus half at square. So with this information, in a two-step process, we can actually solve this problem. That is, let's use equation 2 first. Well, we can't use equation 1 because we don't know time as of now. So what we can do is, let's go to equation 2 and substitute the numbers here. The distance is 100 and the initial velocity is 0. So 0 plus half into 10 into t square. So this gives me 2 into 10 is equal to t square, and this implies that t is equal to 2 root 5 seconds. Well, this was not really asked in the question. What was asked is the velocity. So now I'll plug this information into equation 1, and then I get v is equal to u, which is 0, plus gt, which is equal to 10. G is 10, and now time is 2 root 5 meters per second. So this gives me 20 root 5 meters per second, and the problem is solved. So this stone, when it hits the ground, is traveling with a velocity of 20 root 5 meters per second. Now let's do some approximate calculation. Root 5 is around 2.2, so 20 into 2.2, that is equal to around 44 meters per second. That's pretty quick, right? So yeah, so this is just get a feeler for the number. Now, so why not do these two steps that I just did at a formula level? So whatever I did is to calculate t from here and plug it into this, and that way I eliminate t, and I might get a formula which eliminates t, and may be sometimes useful when we come across problems like this where they are not really interested in time, but some typical question like this is, what's the velocity, right? So let's do this now, and let me do this. It's a little bit of algebra, but that's about it, and it's in fact fairly simple algebra, but it takes a little bit of time. So v is equal to u plus at, and s is equal to ut plus half at square. So let's find out t from here. So v minus u upon a equals to t, and let's plug this value of t into this, and I get s is equal to u into, like I said, it's a little bit of algebra, but we will see, we'll reap the benefits of this. It's going to be an worthwhile equation, v minus u whole square over a square. I hope you realize that I am plugging this into this formula. Now a little bit of simplification will give, let's take the 2a on the other side, so 2as is equal to 2 into u into v minus u plus v minus u whole square. Now this gives me 2uv minus 2u square plus v square plus u square minus 2uv. This gets cancelled, and what I'm left with is v square minus u square is equal to 2as. Right, so here's a new kinematic equation, and the highlight of this equation, I'm going to write it here, is very important: no time. So that's the real key feature of this new kinematic equation. So we got a third equation now in addition to our equations. Now there are various ways of remembering this third equation. So some people remember it like this: v square is equal to u square plus 2as. Now for our purpose it might be nice to write it like this, the way we derived it. Okay, so here's a fantastic equation, and no time, and actually this equation is ideal for our so-called setting the stage problem. So I'm sure you remember the problem: the stone is falling from a building of height 100. So we just put the numbers here directly: 2 into 10 into 100 is equal to v square minus u square, which is 0, and so v is equal to 10 into root of root of 20, and this again I think will give me 20 root 5 meters per second. Same answer as before, but you see that one might want this formula in a ready-made fashion, so that there is no point in doing the problem in 2 steps. So all of a sudden we realize that, hey, this is a nice formula, okay, the third kinematic equation, which has no time. But actually it is more nice than you can imagine, and that's really the content of this chapter. That's how it begins. So once again, let me remind you that we're talking about something called work and energy. We haven't uttered those words yet, but believe me, the key to this work energy theorem is our equation, which says 2as is equal to v square minus u square, which you already seem to know, and I'm going to write a word here, theorem, which we still have to justify. Now watch what I got to do to this equation. I shall multiply both sides by half, so I get as is equal, and also multiply by m, so mv square minus mu square, and there is a half now which I have multiplied by the whole equation. Right, this we're going to, this is f into s, which is the displacement, is equal to half mv square minus half mu square. Now this quantity on the left which has appeared is our definition of work in the one-dimensional world. Okay, right, so work by definition is going to be force into displacement. Actually we're going to be a little bit more careful about this definition of work, but I just wanted to show you how it appears for a constant force and in one dimension. Now this quantity is going to be given a name called kinetic energy. Okay, this is an anticipation of a very much more bigger theorem in physics called the conservation of energy. So you see, now this word has appeared for the first time, energy. And what I see here is the definition of kinetic energy is half m, and it will be better to write it as, I'll justify this, speed square. Okay, it is going to be better to call it speed square rather than velocity square, and you'll slowly realize why I'm so insistent on this. Now this therefore is the final kinetic energy minus the initial kinetic energy. So here we have a grand statement which is a straight result of our third kinematic equation, and a little bit of manipulation where we multiplied by m. And the reason we multiplied by m was because we wanted this quantity called mass into acceleration, which happens to be force, and this is of course displacement. So let's write down this nice statement on the whole board here. Work, we just proved, and that's the key word, we just proved that work done by the external force, okay, work done by the external force. What I mean by external is the external force on the particle is equal to, with the work done by the external force is equal to final kinetic energy of the particle minus initial kinetic energy of the particle. And this is, we have not used any law, we have not, other than Newton's second law, which is F is equal to ma, and we've just used the kinematic equation and we've got the formula. So this is not a law, not a new law, but a theorem that's a consequence of Newton's second law. Okay, and since it's a theorem, it has a proof, and we just finished the proof actually, and therefore we use the word that this restatement is called a work energy theorem, in the sense that it can be proved, the statement can be proved, and the statement goes roughly like this: the work done by all the external forces acting on the particle during its motion is equal to the final kinetic energy minus initial kinetic energy. So there are several questions at this stage. Is this really a useful theorem? Well, that's a big understatement. It's a terrifically useful theorem, as we will see, but just remember that the statement that we've written in this form is always true. There are no exceptions. And why should there be? Because you have just derived it as a consequence of Newton's second law, which we believe is true. And so what is required to use this theorem, we will slowly study. But remember, I just want to point out one thing at this stage, that by all the external forces, and that would imply that you should be well aware of the free body diagram. Okay, so what's next now for us? I'm going to solve a series of examples where you will realize the usefulness of this formula, okay, of this work energy theorem. But I just want to also tell you that there are more general versions of this theorem. And what I mean by general versions is that it's applicable in 3 dimensions. It's applicable, more importantly, to forces that are not constant, and most of all, the work energy theorem actually generalizes, the work energy theorem actually slowly generalizes to a law, perhaps the most impressive of all physics laws, which is the law of conservation of energy, okay, which we discovered slowly. But this is a special form in mechanics. It is not a law, it's a theorem. Within the mechanics, it's a theorem because it follows from the laws of mechanics. But how does it actually generalize to a law of conservation of energy? We will see later. But this, I think, perhaps gives you an idea of the really nice part about this whole topic. So it is better for us to stick to some not 3D but 1D problems, or maybe 2D 1D problems, and with forces that are actually constant. Let's stick to these examples, and instead, with the help of these simple examples, let's try to understand how useful this theorem is. But it might be a good idea to stop by repeating one important point: no time. I think it's a good thing to carry with you when you are studying the work energy theorem, right? So let's stop here, and next time let's look at some examples. All right.